Is the screen visible to anyone?
Yes, sir.
Okay, thank you. So in the previous class, we have seen the summer and subtractor amplifiers, like how we can use operational amplifier for designing an adder or a subtractor circuit. So next we will see is the integrator and differentiator circuits. So here, with the help of operational amplifier, we can implement the integrator as well as the differentiator circuit. So here, the basic integrator and differentiator, if we talk about, so the operation of integrator is like whatever the output we will be getting is an integral of the input with respect to time, and this input will be a time dependent input. So it will be a input that is a time dependent input. We will be getting a this form of relation by using the operational amplifier, that will be behaving like an integrator. Similarly, in case of differentiator, whatever the output that we will be getting is a differentiation with respect to time domain to input that is a time dependent parameter. So this type of relation, if we are able to obtain, that will be behaving like a differentiator circuit. So an integrator and differentiator. So basically we will be going to see this how we can implement this integrator and differentiator. So basic basic integrator. So a basic integrator circuit is a low pass filter. So a low pass filter with an input here and output connected here. Okay, so a basic RC circuit, that is a low pass filter. So this low pass filter behaves like an integrator. That means if we are taking output from the capacitor across the capacitor and it is having an RC circuit, so if we are providing input here and we are getting output from across the capacitor, it will be behaving like an integrator circuit. Okay. So here uh, the problem associated with integrator circuits in this case is like here the RC value should be very high. So if we want to have an efficient integrator, we should be having RC value very high, and also for linear charging and discharging, the current should be constant inside it. Okay, so the second case is for linear charging and discharging, the current should be a constant. So this is the property this RC circuit should be having. So similar concept we can implement by using the operational amplifier. There we will be having the relation like the RC relation will not be such that the RC we would not be uh, uh, having that much effect. That means it's like RC value should not be that much high, and also the linear charging and discharging, that means the current should be constant, that is that can be implemented by using the operational amplifiers. Okay, so this is the circuit of operational amplifier. There resistance, input resistance here R is connected, and instead of feedback resistance we are having a feedback capacitor. So output is the difference between voltage this. Okay, so we are getting the output across this capacitor itself. Okay, so it is the similar implementation of the basic circuit by using RC circuit. So here this is the integrator that we can implement by using the operational amplifier. Sorry. So we will start the analysis of integrator circuit. Okay. So for analysis, we have to assume like the gain, that gain is there, that is infinity, or we can call it like whatever this voltage there, this is Vp and this is Vn. So Vp is equals to Vn and this is equals to 0 because Vp is equals to 0. So here we can call it like the virtual ground concept is eligible because gain is high, then virtual ground is valid. So we will be making virtual ground concept. In that, whatever the voltage of Vp is there, the similar voltage of Vn will be there. So that will be equals to 0. Okay, and also as the input resistance is considered to be very high, the current inside it, so this current will be 0. So all the current that is flowing here, the similar current will be flowing in this way also. So here if it is If, the similar current will be flowing here also, or if the current direction is opposite, the similar current will be flowing. Okay, so we can just remove it. So in the next figure it is given the current direction. Okay, so if the current direction is given, so either way we can consider the current direction, and finally with respect to that only we will be writing the expression, so there will be no change in value. It will be the similar expression will be there. Only if we are taking the current direction in this way, then only the negative sign will be changing. So both the negative signs. Yes, your mic is turned off. Okay. So if the current direction is this way, so here IC is there and the current in this branch will be inside the operational amplifier will be 0. We have already seen. So current will be like the I in, as R input is infinity or very high, the currents inside it, that means suppose this is I1 and I2 is equals to 0. This is the assumption we need to make. Next, by using again the KCL at this node Vn. So at this node Vn, whatever the current is flowing, we need to use the KCL. So by using this, I input will be equals to IC with respect to that. So I input is equals to IC. Now we need to put the value of I input. So I input will be, so the current direction showing is this way. So it is this. That means this is at high and this is at low. So 0 minus V input. So 0 minus V input. Okay. So 0 minus V input divided by the resistance, that is Ri is equals to, so one side, so this Ri is input resistance of the operational amplifier. This is the Ri is input resistance connected to connected with the input voltage that is there. Okay, that is not the input resistance of the operational amplifier. This is different. So it is 0 minus V in divided by R in, that will be I in, and IC. So in case of IC, so IC IC will be there. So IC will be, this is moving from here. So V output minus 0 divided by the resistance offered by capacitance. So resistance offered by capacitance is XC. So in terms of S parameter, it is S into C. 1 by SC is the xc, or in terms of omega, imaginary j omega, c is the resistance, or so we can represent it like the resistance offered by it, so it is SC. Or this similar expression can be like, we need to find out the current. So current in case of capacitance is given as C dV by dt into the difference of the voltage. So difference of voltage here, it will be V output minus 0. The current across a capacitor is given by C dV by dt. So V here is the voltage across this capacitor. So we can just write like the current across the capacitor will be IC will be equals to C dV. V that is voltage across the capacitor. So C dVc by dt. This is the current given by the capacitor. Okay, so the current flowing through capacitor will be capacitor multiplied by change in capacitor voltage with respect to time. So dVc by dt. So similar expression is written here. Okay. So from there, if we just separate it out, we can get like, so V input minus V input divided by R in is equals to C dV out by dt. Okay, so we can just separate because we need to find out the V output. So dV output divided by dt will be equals to minus V in divided by R in C. Okay, so once this is the expression, now we need to find out output. So we will be differentiating or we will be integrating both sides. So by integrating both sides, it will be V output minus V input by R in C dt. Okay, or we can write in terms like V output will be equals to minus 1 by R input C we have taken outside, and we are differentiating integrating it with respect to 0 and t V in, and this V in is a time dependent V input. Okay, dt plus there will be some constants. So there will be some constant. So after integrating we get a constant. So that constant will be with respect to the initial condition if some initial condition is given. So this is because of the initial value of capacitor. So after integration some constant terms are available. So that constant term will be with respect to the initial value of the capacitor. Okay, and also it is showing negative sign, that means the phase will be here 180 degree. That means whatever the output that we will be getting with 180 phase with the input voltage. So whatever input voltage we have applied, the similar output voltage will be in 180 phase shift there will be. Okay, so that's why it is called inverting integrator. So that's why, because it is having negative sign, so that's why it is called inverting integrator. Okay, so I hope you have got the point, like how we need to implement the integrated circuit. So some examples we can consider here. So suppose we have a square wave. Okay, if we have a square wave and we need to find out the integrator. So this is the input and we need to find out the output. So suppose this is plus and we need to find out the output. So once we will be finding out the output, we will be getting the integration of the input. Okay, so integration of the input will be, so here dV out by dt will be minus whatever the input voltage is there divided by the RC. Okay, so this will be, if we do the analysis here, this is nothing but the rate of change of output. So output will be changing with this rate. Okay, or we can call it like this will be the slope of output voltage waveform. So if output voltage, whatever output voltage is there, it will be having a slope of minus V in by RC. Okay, so it will be having a negative slope. So its output will be similar to this. Here its magnitude, whatever the magnitude is there, similar, there will be a slope. So its magnitude will be defining the negative slope. If it is positive, it will be negative. If it is negative, negative will be positive. So now the slope will be positive. Okay, so once the positive magnitude is there, so that slope will be negative. So if negative magnitude is there, the slope will be positive. So this is how the output that we will be getting once we are able to integrate the input. Okay, so from there only we can just see V output by change in V output divided by dt is equals to, that will be a negative value if V input is positive. Similarly, dV out by dt will be a positive value if V input is negative. This is the slope. So if it is negative slope is there, if V input is positive, negative slope is there, that means it will be going downward. Okay, so it will be going downward. And if it is, this slope of the output voltage will be positive, that means it will be going upward when the V input is negative. This is how we will be implementing. Okay, so I hope you have got the point, like how we are going to uh, do the analysis in case of here, and what is the role of V0. So here the initial value of capacitor V0 uh, 0 plus, so this role will be just a DC value. This role will be, it will be providing a DC level to the integrated output. So it will be a DC value. So here we can get, if there is some initial value of the capacitor is there, so it will be providing some DC value. So this DC value will be either positive or negative. If it is positive, this similar graph, output graph, will be shifted upward. Okay, so it will be shifted somewhere upward with a DC value. Okay, so this will be a, you can say, V output that is having an integrated output plus a constant DC value that is there, initial value. Okay, so that will be having higher DC value than this first output. So DC content is higher here. So this is how we need to shift the output. We can shift according to the initial value condition also. What is the initial value associated with the uh, capacitor is there, because the capacitor is, once we are going to use the capacitor, it will be having, it may be like the initial, there will initially there is some charge stored on the capacitor before going to start the operation, so that will be resulting into the initial value, that is V output 0 plus, that is there. So this is your integrated circuit. So the next we will see is differentiator circuit. Okay, so by using the operational amplifier we can implement the differentiator circuit also. So in differentiator circuit, so this is the structure. Here we will be taking the output across the resistance, and it will be having an RC circuit itself. It will be having an RC circuit, but the resistance will be the load resistance, or the load will be the resistance. That means we can just implement it like in simpler way. It will be a capacitor with a resistance, and we will be providing some input. So suppose this input is provided here, and we are taking output from across the resistance. So this circuit is nothing but a high pass filter. So it is a basic high pass filter circuit is there. Okay, but in this case, the to implement the similar, some disadvantages associated with, like we should be having the RC value. Okay, so some limitation on this circuit, because of some limitation we need to use operational amplifier. And here in operational amplifier case, the similar concept, like we will be able to get the output voltage across the resistor, and we are providing the input through the capacitor. So this is how the uh, differentiator circuit can be implemented. So for analysis we again need to see, like, so whatever the Vp and Vn are there, that will be equal, and that will be equals to 0, because this is Vp is equals to 0, and this is Vn, it will be also 0, and the current inside it will be 0. So as we have assumed this, and this will be taking place because of the virtual ground concept. So virtual ground concept will be valid as it is considered as ideal op-amp, and there the gain is high. So when gain is very high, we will be considering the virtual ground concept, and there Vp is equals to Vn. Now again we need to compare the current flowing through it. So if we consider the current flowing through it, so similar, there will be a current flowing through this resistor, and an input current flowing through it. So all the currents here, it is zero current and it is zero current. So again by using the KCL, so by using KCL again we can represent like I input is equals to IR. So once it is I input equals to IR, we will be writing the I input. So in case of input, the current we have already seen, like in case of capacitance, the current is C, capacitance, change in voltage divided by change in time. So change in voltage is the voltage across this capacitor. So it is current direction is this way. So here it is at high and this is at low. So this is your V input. So 0 minus V input. Okay. So 0 minus V input divided by dt. This is the current through the capacitor. That will be equals to the current through this resistor. So this is moving from V output to 0. That's why current direction is this way. So V output minus 0, it will be V output minus 0 divided by R. So this is how the KCL we can implement. So next we can see is just we will be solving. So it will be D, it will be minus D V in divided by dt is equals to V out by RF, or we need to find out the V out. So V out will be equals to minus C into RF d V in by dt. Okay, so again we can just see the relation between input and output. So output that we are getting is d V in by dt. That means the output is differentiation of the input. Also there is a negative sign. So negative sign means there is a phase. So again there is a 180 phase shift. And again the output that we are getting is inverse of the input. Okay, so it is again the uh, inverting, okay, inverting differentiator. Again because we are getting the output that's negative of the differentiation of the inputs, so it is an inverting differentiator. So this is how we will be able to find out the differentiation output. So I hope you have got the concept like how we are implementing. So it is very easy topic. Just we are using the capacitance and resistance to implement the circuit. So capacitance and resistance we are using. So this is all about we should be analyzing the integrated and differentiated circuit. So we can go with the, like, these are the analysis that we have done is an ideal case, like the ideal type of integrator and differentiator. If suppose we want to implement the practical type of uh, integrator or differentiator, we will not be getting the same like a similar analysis. We have to analyze without considering the virtual ground and virtual short concept. But I think in your syllabus that this is uh, only the ideal case of integrated circuit that is sufficient for your analysis. Okay, so next is again an example given here, like how we can implement. So suppose a triangular wave is given, then how we will be getting the output. So in case of a differentiator, we are having an input that is changing between T0 to T1 and then T1 to T2. So between T0 to T1 it is going in positive direction. That means it is having a positive slope. So if it is a positive slope, so from the output that we have just obtained, so V output is equals to minus RFC dV by dt. So from there we can just see, like, if input is positive, so dV in by dt means the slope of the input voltage. So input is this one, the slope of the input is this. Okay, so this is the input slope. So whatever the input slope is positive. So if slope is positive means this term will be positive. So this term will be defining. So in terms of input, differentiation of input is again the slope of input voltage. So if this slope is positive, if the slope is positive, the V output will be negative. And similarly, if slope is negative, the V output is positive. So if the slope of the input is positive, the output will be negative. So that's why the output is a negative, and that will be a constant negative voltage. Okay, and again, if for time duration between t1 and t2, between t1 and t2 it is negative slope is there, so if it is negative, the output voltage that we will be getting a positive. So with respect to the analysis between the time, so for t0 to t1 it is positive slope, that's why between t0 to t1 we will be having a constant output that will be giving out a negative output voltage. So this is how we need to analyze, like how the integration and differentiation can be performed. So this is all about the integrator and differentiator circuit. We can just see some more concept. Okay, so in terms of the integrator and differentiator, here there are different points are there. Actually, I thought one topic we will be like integrator and differentiator we will be completing in one class, so that it will be easy for us for the analysis purpose. So okay, I will be taking some examples related to some integrator and differentiator. Just a minute. I thought I will be taking the example. Okay, let me implement. Just let me uh, copy an example. Okay. So we are having some examples related to that. So just give me 2 minutes. I will be just.
So I think you are on mute.
Yeah. Uh, I'm just giving you out like some examples related to integrated and different. Just I'm not copied and pasted there, so I'm just taking some examples. I will be just give me just five
Okay,
minutes.
sir.
Okay, so just sorry for the disturbance. Yeah, I was just I have not considered the example in case of while preparing the slides. So I have just considered some examples. So this is the example we will be solving here. So this is based on CS. Am I audible? Can anyone confirm whether am I audible
Yes,
or
sir.
not?
Yes, sir,
Yeah.
you are
Okay.
audible.
Okay. Thank you. So here, suppose this is first of all by seeing the connection of resistance and capacitance, we can just differentiate whether it is integrator or differentiator circuit. So as we are having capacitance connected to the output, that means we are taking the output across the capacitor. It is an integrated circuit. Okay. So here the question is we need to we need to determine the rate of change of output voltage in response to the input square wave. Okay. Here the input is shown, input voltage, this is the input voltage, and this is the integrated circuit. We need to determine the rate of change of uh, output voltage in response to the input voltage that we are applying, and then the output voltage is initially 0. So initially it is given like initially output voltage is 0, that means V output 0 plus that we have seen in the into the expression. So this is a 0 given. So if it is 0 given means after integration we need not to add anything. So it is initially given, it is 0. Initial condition is given 0. Okay, and the pulse width is 100 microsecond. So here the pulse width is given to be 100 microsecond. Okay, so pulse width in case of the input 100 microsecond is given. Okay, so we need to find out the rate of change of output voltage. So rate of change of output voltage during the time that is given is that the input is given is plus 2.5 volt. Okay, so in that case if it is positive, at that time the capacitor will be charging. So at that time the dv out by dt we need to find out. In that case it will be the differentiator, that will be V input divided by R input resistance that we are there, and C. So after integrating both sides, this expression we have got, and this expression can be get by just comparing the current flowing through it. So feedback current and the current into this. So I. So by equating I equals to IF, we can get this expression. Okay. So from there, if we have got this expression, we can just by putting the values. So because the magnitude when one is plus 2.5. Okay, so minus plus 2.5 magnitude is there, the input voltage, and RC and uh, R and C values are given. So 10k multiplied by the capacitor, that is 0.01 microfarad. So once we will be solving it, and then we can get, so it is a 10 kilo ohm and this is microfarad, so overall it will be kilo ohms. Result will be negative and it will be in kilo ohms. So it is 10 to the power 6, 10 to the power 8 will be there here. So if we take it, 10 to the power plus 8 will be there, and 3 4, so it will be coming out to 10 to the power 4. So if we will be multiplying, it will be to 25k. So it is 25 kilo volt. Its unit will be, because it is dv out by dt means volt per second will be there. So 25 kilovolt per second, this is the output. That means dv output by dt, that means this is the rate of change of output voltage. So rate of change of output voltage is minus 25 kilovolt per second, or we can just write 25 volt or 25 millivolt per microsecond, because this input voltage is given in terms of microsecond, the pulse width is in microsecond, so we will be, that means the time is given in microsecond. So if time is given in microsecond, we need to put the output also in terms of microsecond. So change in rate of change of output voltage will be minus 25 millivolt per microsecond. Okay, so this is the first part. So if this is the first part, we will just see like it is given out to be like here. If it is minus 20 and 10, because 200 or 100, pulse width is 100 microsecond. No? It is giving me out 200 microsecond. So the pulse width 100 was given. Okay, so if pulse width is 100, it should be 100, I think. So for this 100 time duration, the magnitude is 2.5. If magnitude is 2.5, at that time the rate of change will be minus 25 millivolt per microsecond. So rate of change means the slope of the output. The slope of output means the change of the output. That output is initially 0, and then it is going to negative value, and the slope here, the slope across this we will be finding out. So if we find out the slope, so slope will be change in the this voltage. So this minus this, it will be minus 5. Okay, and then divided by 200 microsecond. So the slope will be volt per second. So slope from there also, what is we are getting, it is it is not 25, it should be, suppose it is 5000 millivolt, 200 microsecond. Okay, so it is coming out to be 25 millivolt per microsecond. Okay, so that means the output that we will be getting is changing with respect to, like, it will be having 25, it is minus 25 millivolt per second per microsecond. So the rate of change of output should be represented by this. That means it is changing from 0 to minus 5, because its overall value is, overall magnitude of the output is minus 2.5 to 2.5. Okay, so that means the overall output voltage, that input voltage that we are applying is 5 volt. So the magnitude change in output will be 0 to 5 volt. Okay, but this change will be for 200 microsecond. For 200 microsecond, we will be getting the slope now minus 250 millivolt per microsecond. Okay, so this is how the slope will be defined. So slope value we have found out on minus 225 millivolt per microsecond. So the output waveform that we will be getting is in this way. Okay, so output waveform that we will be getting is like that. Okay, the next part in that question is describe the output and draw the waveform. Okay, so we need to find the output. So output magnitude, so this is the it is drawn. So the first part was we need to find out this. So we have found out this in the previous part. So now we need to draw the magnitude, draw the output waveform. So to draw the output waveform, we need to find out the magnitude also. Okay, so to find out the magnitude, we will be just considering once the input is positive and once the input is negative. Okay, so when the input is positive, that is at 2.5, so V input is plus 2.5 volt, then the output is negative. So output will be negative because the inverting, if integrator is there, so output will be negative. It is for state. Okay, and it is negative and it will be having a slope. Okay, so output will be negative when input is positive, output will be negative. Okay, when the input is negative 2.5 volt, at that time the output will be positive. We have already seen in the previous slides also. So this will be the output. Okay, so finally if we want to find out the output, so output will be the slope the slope multiplied by the time duration. So time duration is 200 microsecond. So actually the pulse width initially here that is given is, it should be 200 microsecond. Okay, it is given 200 microsecond. It is in the question it is given 100, but it will be 200. So it is whatever the slope we have got, or the rate of change of output, that means dV output divided by dt that we have obtained, that is minus 25 millivolt per second. So in that, if we are going to apply with the time, for what time duration it is going, so that time will be multiplying, then the magnitude will be coming out. Okay, so from there, if we are considering the positive, it will be coming out to be like here. So from there we will be just multiplying it. So it is it will be coming out 5 micro it will be cancel out, and 25 multiplied with this, it will be 5000 millivolt, that means 5 volt. Okay, so V output will be coming out to be 5 volt. Okay, so during the time of input is at plus 0.5 volt, the output will be going from 0 to minus. So that means because there is a negative slope is there, so magnitude of the output will be 5 volt. That means initially it will be 0, and then it will be going to minus 5 volt. Once it is minus 5 volt, again for positive slope it will be going from minus 5 to 0. That means there will be a change of 5 volt will be taking place. So whatever the range of input is there, that range of input will be the range of the output that we are getting, but it will be between 0 to minus 5, and then minus 5 to 0, and then like that it will be changing. Okay, so this is how we will be getting the output waveform. So one part we can just take. So suppose this similar, in the similar question, just modify the integrator. Okay, integrator circuit to make the output changing between 0 to minus 5 volt in 100 microseconds. Suppose the similar you need to find out, like if the output is changing between 0 to minus 5 volt for 100 microsecond. Initially it is changing in 200 microsecond. If we need to implement the waveform that look like it is changing between this and this, time duration is 100. So what we need to do on the circuit point of view to get the output like that? If you want to find out this as the output, what will be the input changes we need to make? Just you can just go with it for your homework part. Okay, so the next is the differentiator, example of a differentiator circuit. So here it is given, a differentiator circuit is given with an input. So we need to draw the output with respect to this, by considering the operational amplifier is an ideal one. So if we want to find out the output, so in case of differentiator we have got the output. So in case of differentiator, this is R in into C dV in by dt. This is the output that we have got in case of differentiator. So this is the input waveform, and we need to find out the output waveform. So we can just see the output will be the slope of the input. So slope of the input multiplied by this R and C. So R and C will be multiplying. Okay, and with respect to that, so here R in, sorry, RF will be there, C in will be there. Okay, so RF and C will be multiplying, so it will be 0.001 microfarad multiplied by 2.2 kilo ohms. So from there we will be getting 2.2 micro, this is nano, and K. So again it is micro. So this will be a micro. This multiplication is, this is called time constant. This is called RC is called time constant. So that means its unit will be in seconds. Okay, so it is RFC will be 2.2 microsecond. So this is we have got, and now the slope of the input. So slope of input will be multiplied by this, we can get the output. So slope we will be finding out. So it is 0 to 5 microsecond is there. So total is 0 to 5 microsecond. This is there, and change in magnitude. So change in magnitude is like 5 minus 5, that is 10. 10 divided by 5. Okay, so 10. This is final one. This is okay. So 10 minus this, that means 2. 2 is the slope. Okay, so V output that we will be getting is 2.2 microsecond. Okay, multiplied by slope will be output, that is 2 volt divided by microsecond. So microsecond will be cancelled out. It will be 4.4 volt. So V output will be 4.4. Okay, so if the slope is positive, the output will be plus 4.4. If the slope is negative, it will be minus 4.4. So with respect to that, if we just get the output that we will be getting is for 0 to 5, the slope is positive, so the output will be negative. If the slope is negative, the output will be positive, the magnitude will be plus minus 4.4 and plus 4. So this is how we will be finding out the output. So I hope you have got the concept, like how we need to analyze the circuits of integrator and differentiator, and with the help of examples also we have seen. So till now, if anyone is having any doubt, you can just ask. किसी को कोई डाउट इसमें?
No, sir.
Okay, then thank you. So sorry for the disturbance. Actually, I have not included the questions. That's why it was time taking like. So thank you. Yeah.
Thank you, sir. Okay, thank you, sir.
Thank you, sir.